Hey, welcome everyone to the QFT parallel session on the last day. The convener for this session will be our first speaker, who is Christopher Beem. He's going to talk about hidden unitarity in the SCFT VOA correspondence. So,
okay.
I'll give you the floor.
Great. Thank you. Thank you, Fredrik, for the introduction, and to the local organizers for the invitation to convene and to speak here. I'm going to be describing some work in progress, hopefully near complete, with Arash Ardehali at Stony Brook, Leonardo Rastelli at Stony Brook, and Madalena Lemos in Durham. And it's a chapter in this SCFT VOA correspondence that's in the title. So this is now an old story, although it's all I've been working on for a long time. There's some correspondence that I'm going to review that we discovered back in 2013 between four-dimensional n equals 2 superconformal field theories and certain classes of two-dimensional vertex operator algebras, VOAs. And this has been a, we think, fruitful thing to understand better. It's been useful in terms of arrows going in both directions. It's been some sort of organizing principle for things that you might care about if you're a sufficiently supersymmetric person in these 4D n equals 2 theories. And it's also been interesting from a mathematical point of view because it's shed some new light on these vertex operator algebras that quantum algebraists and geometric representation theorists and people like that have some interest in. And one of the striking features of this correspondence that's been apparent from the very beginning is that unitarity is somehow a casualty of the correspondence. If you start out with four-dimensional unitary theories, the vertex algebras that you end up talking about are not unitary in the usual sense. And this talk is about trying to understand that casualty better. And so my plan is to give a recap of this construction of the correspondence, outline a structural story about how unitarity does, in some sense, survive the map from theories to vertex algebras, and then outline some partial results, trying to leverage this sort of new version of unitarity for the vertex algebras that show up on the right-hand side into some sort of a classification, and I'll conclude with some remarks at the end. Okay. So the setting for the construction is sort of the bootstrappy point of view of thinking of 4D n equals 2 theories in terms of an algebra of local operators. So the main object is some sort of Hilbert space of local operators that you assign to the 3-sphere. So this is something like the space of local operators that can be inserted as at a point. And these things live in some representation of a superconformal algebra, which, if you complexify everything, is just SL4/2. And, okay, some people are probably happy with that superconformal algebra. If not, then the main players inside of that algebra that are important in this construction are an SL2 times SL2 bar geometric action that act as holomorphic and anti-holomorphic Mobius transformations on some complex plane C with coordinates Z and Z bar living inside of R4. And then complexified versions of rotations in the transverse plane and the U1R symmetry and the SU2R symmetry. And these things organize the space of local operators into irreducible representations, which are labeled by quantum numbers with respect to some Cartan generators of all of these things. So I'm going to use a basis where operators are labeled by H and H bar, which are sort of L0 and L0 bar weights with respect to these holomorphic and anti-holomorphic SL2s, a spin quantum number that has to do with rotations in the transverse plane, and R charges, little r and big R. Okay, and then probably everyone has seen many of these pictures before. The algebraic structure on this vector space comes from the operator product expansion, which is graphically something like this. You take pairs of operators and you multiply them. You express the Euclidean time evolution on this ball in terms of a state on the sphere, and then re-expand that state into a basis of states corresponding to local operators at the origin, and you get some schematic X-dependent operator product expansion OPE algebra. And this whole thing has to be covariant with respect to the action of the superconformal algebra. So in sort of a slick word, you'd say that you get some sort of equivariant OPE algebra with respect to the action of the relevant superconformal algebra. And that's the setting in which you can do some sort of cohomological tricks, which are, at least in principle, sort of standard in the supersymmetry world. So you take your superalgebra, you look at the odd elements, so the fermionic generators, which are usually called Q's and S's in this case. You look at elements of that superalgebra that are nilpotent, so that square to 0. So I'll be calling them in these slides D for differential. And then if you choose such a nilpotent differential, which is homogeneous for some even symmetry, so if it's graded by something in your Cartan subalgebra, then you can give this whole thing the structure of a differential graded OPE algebra, which just means that you keep track of that grading. You think of this nilpotent supercharge as something that squares to 0 and gives you sort of a chain complex structure on the vector space, and you pretend that you're doing homological algebra. And then there's sort of a general story in that sort of DG setting. You care a lot about the symmetries that are in the commutant of your differential, so things that are sort of Q exact, and you also care, things that are commutant, so they're Q closed, things that are in the centralizer of your differential, and things that are so-called Q exact or D exact, so that are commutators of your differential with some other generator. And then the general story is that with this sort of formalism in place, if you pass to cohomology, you're always going to get something which inherits some sort of OPE structure, which now is invariant under the exact symmetries and equivariant, meaning it somehow transforms well under the closed symmetries. And with that sort of abstraction in place, then you have a game which is just to go and look at different nilpotent differentials and see what sort of a OPE structure you're going to get out when you pass to cohomology. And this is what we did in 2013. And it turns out that there's two, up to some sort of equivalence relations, there are two distinct nilpotent differentials that I'd call D and D check, that have the property that the holomorphic Mobius transformations, the SL2Z, is preserved, and some twisted version of the anti-holomorphic SL2 transformation, so I've called it SL2 hat. This is the diagonal subalgebra generated by the SL2 bars, and your internal SU2 R symmetry. Those are exact. And as a consequence, when you pass to cohomology, you're going to get some sort of SL2 covariant and SL2 bar invariant OPE algebra, and actually, whether you use D or D check doesn't matter. You get the same, you get an isomorphism between those two constructions. And so this is also known as a meromorphic OPE algebra, because you see the SL2Z, you don't see the SL2Z bar, as long as you use this twisted version. This is also known as a chiral algebra to physicists. It's also known as a vertex algebra. So that's the machine. And in a little bit more detail, you can ask, what does the output of this machine look like? So at the level of the vector space, so at the level of local operators, it turns out that the cohomology classes can be identified with the set of so-called Schur operators. So this is a set of operators that obey two linear relations on their quantum numbers, which I've written here. So the anti-holomorphic scaling dimension H bar is related to the SU2 R charge, and the transverse spin is related to the U1 R charge. And so you go from a 5-graded vector space to a 3-graded cohomology. And these 3 gradings can be thought of as a conformal grading on your vertex algebra. So this is like the usual conformal grading in a chiral algebra. The U1 R charge acts as a kind of cohomological degree. And then there's this extra SU2 R grading, which is somehow additional, and its role is to be determined. And some technical fact which is relevant if you're really trying to keep track of the details is that the operators that obey this condition are always of the form some superconformal primary operator acted on by a bunch of derivatives in the z direction, and they're always in the highest weight state of their SU2R representation and have some definite positive helicities if they have any spin. The fact that they're SU2 highest weights is important. Okay, and And then to get a vertex algebra structure, there's supposed to be some OPE that you see on this space. And now the rule is that because we're working in cohomology with respect to this differential, if I want to move operators around, I need to use symmetries that were compatible with the differential. So if I want to put an operator at a point z, I need to move it using the SL2 generators that I was allowed to use, those commuted with the differential, and the SL2 hat generators, which are a combination of del z bar, L minus 1 bar is del z bar, and the lowering operator of the SU2R symmetry. And that means that in practice, if you're treating things in terms of actual operators in your 4D theory, if I want to move an operator to some point, I have to take that highest weight Schur operator I started with and add a definite set of corrections which depend on z bar and that come from acting with the SU2 lowering operators. And so this rule for moving operators around violates the conservation of this extra R grading. And so this extra quantum number that we had around, this sort of third grading on the vector space, is something that you don't expect to really see at the level of the vertex algebra because you violate conservation when you move operators around. But you can still get a little bit of structure because even though you violate our conservation, you always lower when you move things around. And that means that instead of keeping track of a grading, you keep track of a filtration. So we define something called the R filtration on the space of Schur operators, which just means that instead of taking a decomposition into graded subspaces, you take an increasing nested sequence of subspaces where you look at all of the operators whose R charge is less than or equal to some number. And it turns out that this algebraic structure respects that filtration in the best possible way. So there's a theory of filtrations on vertex algebras that I won't talk about, but there's a notion of a good filtration on a vertex algebra, which in particular means that when you take the OPE of two operators, which are in filtration degree P and Q, it should live in the filtration P plus Q piece, but the singular parts should live in the P plus Q minus 1 piece. So if you want to have singularities, then you always lower the R charge by at least 1, is the idea. That's some technical fact, but it makes it so this is sort of the right way to define a filtration on a vertex algebra. Okay, so before going on with any abstraction, I'll give the two standard examples just so you can see what's really happening under the hood if you haven't seen this before. The basic examples are free field theories. So if you take the free hypermultiplet, the relevant Schur operators are just free complex scalars, Q and Q tilde. And in terms of this basis of quantum numbers I'm using, those have holomorphic conformal weight 1/2, SU2R charge 1/2, cohomological degree 0. They have the usual free field OPE. And they live in SU2R multiplets like this. So Q and the complex conjugate of Q tilde, and Q tilde and minus the complex conjugate of Q live in the SU2 doublets. And that means this rule for moving operators around tells me that I need to take a linear combination, depending on Z bar, of Q and Q tilde star, or Q tilde and Q star. And then when you take the OPEs of these, just using the free field OPE of the four-dimensional fields, you get this 1 over separation norm squared in the denominator, but then you get explicit Z bars and W bars in the numerator to cancel out the anti-holomorphic dependence. So that's where you get this sort of miraculous meromorphicity, is just from some sort of systematic explicit cancellation of anti-holomorphic dependence in denominators and numerators. And this OPE, if you're a vertex algebra person or a chiral algebra person, defines for you a symplectic boson or a symmetric beta gamma system. Similarly, for a free vector multiplet, the relevant operators are some free Weil fermions. I won't narrate all the equations this time, but if you go through the same exercise, you again get some sort of systematic cancellation of anti-holomorphic dependence, and you get the so-called symplectic fermion, or small BC ghost OPE. So these are the simplest, non-unitary, free vertex algebras. So if you recall from string theory, since this is Eurostrings 2024, when these ghosts show up on the world sheet, there are some sort of non-unitary things that come from gauge fixing. Okay. Beyond free fields, there's some structural things that happen when you have symmetries in your 4D theory. So there's this sort of song and dance that happens over and over again a few times. In 4 dimensions, you have a stress tensor operator if you have a local theory. It has a super partner, which is actually a component of the SU2R conserved current. Some component of that is a Schur operator. That thing gives you an operator in this Q cohomology, and that thing behaves like a Virasoro stress tensor. And the OPE here is fixed by conformal Ward identities after you put in all of the relevant Z bars and W bars. And you recognize that as the OPE of a Virasoro algebra with a central charge, which is minus 12 times the 4-dimensional C central charge. And famously, in unitary theories, the 4-dimensional C central charge is positive. So that minus 12 is a real minus sign. And so that means that you're getting negative central charge Virasoro algebras. So this is a non-unitary Virasoro algebra. Similarly, if you have some global G symmetry, then the conserved current multiplet includes some moment map operators that become Schur operators whose OPEs are fixed by conformal Ward identities, and they give you the affine Kac-Moody vertex algebra OPE, where now the level of the Kac-Moody algebra is minus a half times the 4-dimensional level, where again, this is a convention where 4-dimensional levels are positive for unitary theories. So the minus sign is real. And I won't say anything else about it, but when you have extra supersymmetry in 4 dimensions, that realizes itself as extra supersymmetry in 2 dimensions as well. Okay. Now, generally, the vertex algebras coming out of this machine are more than just these Virasoro or Kac-Moody symmetries. That just comes from looking at some particular set of operators. There are usually some sort of extremely nonlinear W algebras that didn't have names before they started being associated with these 4D theories. But in some select cases, the Virasoro or Kac-Moody structure is enough to determine everything. This is an empirical observation. People have been able to compute enough things to sort of infer what the right description is in various examples. And so, because these are going to come up again later, I'll mention that there's 2 series of so-called Argyros-Douglas SCFTs, the A1 A even and A1 D odd for people who are in this world. If not, those are just names, where the associated vertex algebra is exactly some particular set of Virasoro minimal models. So this is the 2 comma odd minimal models. That's one series of non-unitary minimal models. And for the Kac-Moody case, you get some interesting fractional levels known as boundary admissible levels. So these are not the best case for physics. These aren't sort of unitary minimal models, and they aren't sort of integrable Kac-Moody, but they're still things that representation theorists are interested in. And empirically, just by looking at this list, we see that there's only certain central charges that are showing up. There's a whole bunch of non-unitary minimal models, the P comma Qs where Q is not equal to P plus 1. But it's only these 2 comma odd ones that are showing up. Similarly, there's a whole bunch of so-called admissible levels for Kac-Moody, but you're just getting the boundary admissibles here. And so one question that we've been wondering for a while is whether there's some sort of structural reason why those are the only things you could have found. And maybe I'll say something about that in time. And so the approach is to try to get some angle on this and some structural angle by thinking about unitarity. So these are non-unitary vertex algebras in the traditional sense, so what happened? In 4 dimensions, one way to witness unitarity for an SCFT is to look at positivity of certain 2-point functions. You have an involution on the set of local operators in any unitary theory, which comes from actually treating them as operators or operator value distributions on Hilbert space and taking the adjoint. So you have a star involution that squares to the identity. And using that, you can set up some sort of reflection positive configurations for 2-point functions and demand that they be positive. So this is, we're in Euclidean signature, but this is unitarity via reflection positivity. And the simple issue is that this structure isn't something you see easily when you've passed to cohomology the way I described before, because this star operation takes Schur operators and gives you some sort of conjugate Schur operators that are not the same thing. And in particular, if you take an operator where you've labeled all of its quantum numbers and act by the star involution, you get something whose conformal dimensions are the same, spin is flipped, and R symmetries are flipped, and the important thing is that the SU2R charge is flipped. So that green highlighted quantum number is a failure of this operator to be another Schur operator. So you are taken outside of the sector where this vertex algebra structure lived. Okay, but there's a relatively simple fix to that, because if the issue is that I started out with an SU2 highest weight state and I ended up with an SU2 lowest weight state, then I can rotate it back to an SU2 highest weight state. So I just need to define an improved version of this star automorphism, where I take an operator, I take its adjoint, and then I rotate it by 180 degrees in R symmetry space. That gives me something which now squares to an R parity operator. It doesn't necessarily square to the identity, but that's the object which is going to send Schur operators to Schur operators. And in fact, a nice technical feature is that it intertwines the action of these two differentials I had before, the D and the D check. And precisely because of this property that you can just go and check, it means that if you are taking the OPE of two operators and you do this conjugation, it's the same as doing the conjugation first and then doing the OPE up to replacing Zs with Z bars, up to some, this is the sort of fact that there's a reflection in Euclidean space. So this is actually defined some sort of vertex algebra automorphism. And so a punchline at a structural level is that the vertex algebras coming out of this procedure are not sort of bare vertex operator algebras, but they're equipped with this sort of canonical automorphism, which should know something about unitarity. And we can make contact with unitarity and reflection positivity by doing some algebra. And for reasons of time, I won't narrate this equation, but just to say that you can define a sort of two-point function on operators where you include the action of this conjugation instead of the action of star that you would have previously. And then you unpack all the definitions, and you end up with a rule, because this thing is supposed to be some particular power of Z bar times something which is positive for a reflection positive configuration. It allows you to assert what sort of a coefficient you should have in the two-point function in the usual way of writing chiral algebra two-point functions. So if the two-point function of this thing is some coefficient over Z to the appropriate power, that coefficient needs to be this phase, I to the 2h minus r, which if for simplicity you only think about bosonic operators, then this exponent is always even, and then you get minus 1 to the h minus r. And so you get definite signs if you know R charges. So if you know how this conjugation operator acts, and you know what the R charges are, then you're required to get certain signs for two-point functions if your 4D theory was unitary. This is a non-trivial fact. You can just, if you know all of these things, you can just take your Virasoro algebra and start computing two-point functions and check whether they have the right signs, and they might or they might not. Okay, so there's some new version of positivity, which I've been calling filtered positivity, which involves knowing the R grading and then imposing these sign rules. Okay, so in my last 5 minutes, I want to describe trying to take that structure and ask to what extent is it compatible with the vertex algebra coming out being some simple vertex algebra we know everything about, like the Virasoro algebra. So suppose we're in a case where some hypothetical 4D SCFT has the Virasoro algebra as its associated vertex algebra with some central charge C that's unknown. Is that central charge constrained by this unitarity structure? We know that if it was an actual unitary theory, we know the answer, right? C is either 1 greater than or equal to 1 or one of the unitary minimal models. But what about this other structure? What are the possible values of C if we impose that? And you can do some very brute force analysis at low levels. Let me be a little bit quick about it. So you can just write down some particular operators where we happen to know what their R charges are. It's some fact that I've not explained, that the stress tensor itself, we know what its R charge is. It's R equals 1. We know all of these things, how they act on it, and so you can just do this computation and check. And you find out that this coefficient, which is the 2D central charge over 2, is supposed to be negative by this sign rule. So indeed, the central charges which are always negative always had to be negative. You can look at some standard level 4 operator. This is the first quasi-primary at level 4. And that thing has to have R charge 2, because if it had R charge 1, you would be in a free field theory because it would be some higher spin conserved current in 4 dimensions. That's some extra fact I have to know. And then doing the same calculation, you find out that there's this quantity here, which is a polynomial in C, that has to be positive. And that tells you that the central charge not only has to be less than 0, it actually has to be less than or equal to minus 22/5, which is the 2,5 minimal model level. So you're getting some constraints on central charges that could have come from 4D. To keep going, you have to know more about R charges. In particular, I mentioned earlier that the way that we know about R charges is through this filtration. So there's some filtration I should have on the vertex algebra that allows me to read off these R charges, that allows me to check these signs. Okay, and here is, we have a bit of a shortcoming. I'll mention it again at the very end, I think. But for the present slide, I'm just going to assert that there's a standard filtration, which is a good candidate. So what follows is going to be an argument subject to the assumption that this is the way that I assign this R filtration. And this is the dumbest thing you could do. The stress tensor had R charge 1, so when I write down things which are normal ordered products of stress tensors, I just count how many stress tensors there are, and I say that should be the R charge. That's an obvious guess. But because of this rule about sort of translations lowering R charges, it's in the filtered sense. So I say if I write something which is a product of 10 stress tensors, then it has R charge less than or equal to 10, and so on. And if you give me that assumption, then we actually can prove a theorem, which is that the Virasoro algebra at central charge C, with that filtration, and with this conjugation operation acting the way that it does, can only satisfy this filtered positivity condition for the 2, odd Virasoro minimal model levels. And this is some calculation basically at the level of comparing signs. So we care about signs of 2-point functions, and so we can go look up the Katz determinant that gives me the products of signs of 2-point functions. And I can read it off from a textbook, and it gives me the determinant. And then you can compare that with the sign that you're required to get by this procedure. And omitting details, you find out that if any of these factors are negative, or if any of these factors are positive, it has to be an even number of them that's positive in order to match signs. And then you write out what this product of monomials looks like, and it looks like this. It's C minus C2 odd times a product of factors which are greater than C2 odd. And you'll have to trust me because I think, well, I wouldn't be able to do this as fast as I'm going. But this means that if your central charge is less than the C2, 2n minus 1, then it has to be less than or equal to the C2, 2n plus 1. So basically, if you're to the left of 1C2, odd, you have to be all the way at the next one. So this kills the gaps in between the C2, odd minimal models. That's what this argument does for you. And with 2 minutes left, let me say that an analogous argument applies in the case of SU2 affine Kac-Moody algebras. There, things are a little bit tricky because you have to treat the stress tensor in a special way. Because the stress tensor is built out of currents by the Sugawara construction, and this means that all of the calculations are slightly trickier. But the same logic applies. And again, with some assumption of a standard filtration, you get a theorem question mark because we haven't finished dotting the i's, which tells you that that structure can't be filtered positive except for these boundary admissible levels. So at least with some assumptions about these filtrations, you're actually deriving the set of vertex algebras that are the ones that we've seen, quote unquote, in nature in these Argyros-Douglas theories. That seems to be the reason that those were the ones that were showing up. Okay. So I should finish by commenting on this issue of assuming the filtration. This would, of course, be a more compelling story if I didn't need to impose how I was assigning this R filtration. Because you could imagine that if it's just an issue of signs, maybe I just need to adjust the assignment of R charges here and there, and I'll correct for the wrong signs in this argument I just gave. It turns out that this good filtration rule, which tells you that when you take the OPE, the R charge has to decrease, combined with this filtered positivity condition, seems to be a strong constraint. But it's a bit tedious to impose. So you can start trying to bootstrap the filtration by working your way up to higher and higher dimension operators and imposing both this goodness condition and that the signs work. And it starts constraining your R charge assignments in some strong way. And there's some indication that if you require that the R symmetry grading on your whole vector space be unbounded above, which is we think a physical consistency condition that's required, then you might end up actually bootstrapping your way into the standard filtration. But this is future work because it at the moment is a little bit uncontrolled and tedious. But that's where we hope things might work. Okay, so I'm at my time, so I'll just leave summary comments on the board for anyone who wants to read them, and I'll be finished and take questions. Thanks.
Thank you. Questions?
Some bound on C from this consideration. Do you think there is something similar for A in some way, or some relation between A and C? Some bound on their ratio?
Not that would follow from anything closely approximating this analysis. There's some relationship, there's some dialogue between the vertex algebra story and the A central charge when you look at high temperature limits and sort of connections with, there's some story with modularity that I think you might already know. But like that, the way you're accessing the value of A is so indirect that I don't know how to compare it to these sort of structures.
More questions?
Can you say again, why did you focus on these Argyres-Douglas examples?
It was just for simplicity. There's a general story of a structure. So any example where if you have any control over the vertex algebra at all, this sort of structural story has to hold. You need this involution, you need this filtration, so that if you then do the Gram-Schmidt orthogonalization and find graded components, you get these sign rules being obeyed. It's a bunch of extra stuff that has to be true, and it's not obvious that it's true in any example at all. Even the examples that I didn't rule out are not ruled in by this procedure. So I ruled out everything except the 2 odd Virasoro, but the fact that this structure does hold with all the correct signs is a much more refined thing, because I was ruling things out by getting a wrong sign overall. But to rule things in, you would need the whole signature of the matrix of inner products. So the structure is there always, and then for this sort of proto-classification program, just the simplest thing to start out with is Virasoro and FN Katz. I mean, this is where you have like Katz determinant results for matrices of inner products, whereas if you take like class S theories or something, we basically don't know anything about their vertex algebras.
Okay, if there are no more questions, we thank Chris again.